Imagine proving you know the combination to a locked box without opening it or revealing the code. That's the core intuition behind zero-knowledge proofs. Truth can be verified while secrets stay hidden. This idea supports both blockchain privacy and scalable ZK rollups. So far, we've seen why scaling is hard. Block space is limited, demand raises fees, and throughput is capped when every node processes every transaction. Ethereum increasingly provides security and finality, while Layer 2s improve speed and cost. Now we'll look at how ZK proofs let rollups prove that off-chain work was done correctly. Zero knowledge changes what it means to prove something. Instead of revealing the secret, the prover creates evidence for a specific public claim. The verifier checks that evidence and accepts or rejects the result, without seeing the private input or rerunning the full computation. Trust shifts from show me everything to show me a proof I can verify. That separation is what makes ZK useful for privacy, scale, and sensitive data. Think of it like a locked door. I claim I know the code, but I never say it out loud. Instead, I enter through one side and come out the other. You can see that I must have opened the door, so my claim becomes believable, while the secret stays private. For a zero-knowledge proof to be useful, 3 guarantees have to hold together. Completeness means true claims can be proven by an honest prover. Soundness means false claims cannot be made to look true, except with negligible probability. Zero knowledge means the verifier learns only that the claim is true, not the secret behind it. Together, these properties create trust. Valid participants succeed, attackers are blocked, and private information stays private. Zero-knowledge systems split the work between 2 roles. The prover does the heavy lifting. It has the private witness, runs the full computation, and produces a compact proof. The verifier does not repeat that work. It checks the proof against the public statement and returns accept or reject. In a ZK rollup, the rollup prover generates the proof off-chain, and an Ethereum smart contract verifies it on-chain. A helpful way to read any ZK system is to separate the public claim from the private reason it is true. The statement is what anyone can check, such as whether a transaction batch follows the rules. The witness is the underlying data or computation that supports that claim, but should remain hidden. Proof generation turns the witness into a small cryptographic proof, which the verifier checks alongside the statement without learning the witness itself. The key difference between proof types is timing. In an interactive proof, the verifier asks challenges and the prover responds, often across several rounds. That works when both parties are online together. Blockchains work differently. A proof may be posted now, then checked later by smart contracts, nodes, or users. Non-interactive proofs package everything into one standalone object, which is why ZK rollups usually rely on them. Here's where the scaling benefit appears. The rollup handles the heavy work away from Ethereum. It collects many user transactions, executes them, and computes the new state. Then a prover creates a compact ZK proof saying, in effect, this batch followed the rules. Ethereum does not replay every transaction. It checks the proof. If the proof is valid, the state update is accepted, reducing on-chain computation while preserving Ethereum-level security. Zero-knowledge proofs can also prove that a requirement is satisfied without exposing the details behind it. That might mean proving eligibility, balance, or compliance, while keeping identity, account history, or sensitive documents private. One distinction is especially important. A zero-knowledge proof can prove correctness without making the whole system private. In many ZK rollups, the proof shows that a batch was processed correctly, but transaction details may still be public for data availability and verification. Privacy proofs are different. They are designed to hide sensitive inputs, identities, amounts, or outputs. So remember, ZK enables privacy, but privacy only happens when the protocol deliberately conceals data. In practice, a ZK proof usually works with 2 kinds of inputs. Public inputs are the claims everyone is allowed to see, such as the old state root, the new state root, or batch metadata. Private inputs are the hidden details the prover uses to support that claim, such as transactions or user secrets. The proof acts as the bridge. It convinces the verifier that the public result came from valid private computation, without exposing the private data. Succinctness means the verifier does not need to replay the whole computation. A prover can process thousands of transactions, do the heavy cryptographic work, and output one compact proof. Ethereum then checks that proof instead of re-executing every step. This shifts cost away from the chain, where computation and storage are expensive. The proof is small and quick to verify, even though creating it may still require serious off-chain effort. Before accepting any zero-knowledge claim, run a reality check. What exactly is being proven, and what information still stays public? Who pays the cost to generate the proof? Has the circuit and implementation been audited? Does the system depend on a trusted setup, special hardware, or external infrastructure? And if the underlying data is unavailable, can anyone still verify the full story? ZK improves privacy and verification, but it does not remove engineering trade-offs. The core idea is simple. A prover can convince a verifier that a statement is true using a witness without exposing everything behind it. In rollups, that usually means validity, not privacy. Next, we'll connect these proofs to sequencers, provers, contracts, state, and the full transaction lifecycle.